So hi everyone, welcome to a new Grace Code Thursday. So today I will present to you modern C++ CPU computing with a CD algorithm. But before I will present to you the team, the organization team of the school and of the Grace Code Thursday. So I work with Karim and Marie. They are in TerraTech and they run the competence center, French competence center of HPC, HTC, HPDA, AI, and quantum computing. And we made this school last year together. It was a really a success, and we want to continue here for the next part. So we had the school in 2024. So it was the second version of the school we had with my dream team in 2023. And then we expand it with all the advice from TerraTech, from Marie and Karim mainly, to scale up this school up to 500 people trained on ANSI and 12 satellite sites spread over 4 countries. So it was a 2 weeks school, intensive school for people who attended the school in ANSI at LAPP. So you can here the picture. See the picture here. We have 9 amazing teachers running their lectures on this school. Everything is interconnected, so all the time we are talking about one other lecture to if you want to go deeper in this field. It's normal. It was a success, and so this year we start this. It's the same, but we go in English. It was a French school. We get all the lectures available on YouTube. So if you want to have a look, it's possible. You have 60 hours of videos in French, but if you want to get an idea of what's going on in this school, you will have a nice idea. We have all the lectures available on containers. So if you want to run them with Podman, Docker, Aptainer, whatever you want to use, with Kubernetes, with Docker Swarm, with OpenStack, you can use them if you want to you. You can also be a satellite site if you are interested in. So the idea is to provide a room to get some people to train them. So it could be your colleague, it could be other people. You can choose whatever you want to do. And then we will restream all the school live. You can restream it yourself also. And you can form your people, train your people, and make some publicity about your site and say, okay, we can exist, maybe we can work together to do some stuff together. So it's really interesting to have this in mind. You can also follow the school a la carte, and because we split the school with basically 1 day per language, with several technologies in it, but 1 day per language roughly. So you can pick what language you want to use. Of course, you will miss lots of interesting stuff. I don't want to lie to you, but if it's better for you, because 2 weeks it's a long school, of course, you can have that. We will get all the video online, and we can follow also on Discord the school for that. So let me play for you the trailer of the school of 2025 for this summer.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grey Scott School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Cycle, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, CuPy, CUNumeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G-Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So that was the trailer. So if you have some question, we can ask them at the end of the presentation. So don't hesitate to ask some question about that if you're interested in, or to contact Mary or Karim or me by mail if you are interested to be part of this school. And now I will give the floor to myself to present to you this modern C++ CPU computing with STD algorithm webinar. So to introduce myself briefly, I'm Pierre Aubert. I work at LAPP, so Laboratoire of Particle Physics. I work mainly on the school right now because it's really time consuming to prepare such a school. But besides this school, I work also on CTA, which is an astrophysics experiment which will be involved in analyzing lots of telescope data, so big telescopes with a lot of captors with time response, a lot of data to analyze on real time. So I'm a lead developer on the real-time analysis project on this experiment. So we are still in development mode, but we have a version which is already deployed since several years now in production. So we keep adding stuff in it, but it's a work in progress which is working. And my job in this analysis is to make sure that everything is as fast as possible and maintainable, of course, also to be sure that everything is nice. That's why there is maintainability lectures or unit test lectures or stuff like this in this school, because it's something really important. It's nice to compute fast, but if you cannot change what you did, or you cannot update what you did, or you cannot maybe have a look and get some internship on it to work with, it will be a problem at some point. So it's important to take care of the design, take care of the test, take care of the documentation, and that's I do that for CTL right now. But the idea is to try to spread all this practice for all people who are interested, because it's important to do that. So I give the floor to myself again, and I wish you a nice webinar. So let's talk about C++ algorithm. So I will briefly introduce that. So the point of this presentation is to give you an overview of C++ algorithm, but not only, of course. We will start before that. So as an introduction, I will say here we want to mainly develop applications. And we want to develop an application, but we want to ensure performances, especially in terms of computing. So that's not really trivial, as you could see in the previous webinars, but that's possible. Okay, that's possible. But moreover, after that, we want scalability. So we want to increase the number of cores, the number of CPU, maybe to use CPU and GPU both at the same time, or to extend in multiple nodes. And that's really difficult. Let's be honest, it's quite difficult. And moreover, on top of that, we want portability, because maybe I want to use Intel, AMD, and ARM CPU, and maybe I want to use NVIDIA and Intel and AMD GPUs. And it's not the same purpose, it's not the same size, it's not the same computation power, and quite difficult also to do that. It's really difficult. But the most difficult part of everything here is to do all of that, but with less development as possible, so with less code as possible. That's the very problem that we are facing, because the more code you develop, the more code you have to maintain, and every time you want to add the functionality, you have to duplicate the work for all the backend that you want to use. So it's definitely the biggest problem that we want to face. And of course we want to do that, but we want to keep performances, we want to keep scalability, we want to keep portability, so this is really difficult. And to do that, we want to do that efficiently, so we don't want to code right now, we will just do some conception before that. And let's take a look at the parallelism. So first, once you want to have performances, you want to express parallelism. So for example, in my case, I have an event to treat. So let's say it's an event of a telescope or multiple telescope. If you are in different experiments, maybe you have energy in a calorimeter or stuff like that. And I'm very lucky because I have event, but I have a lot of independent events. So they are stochastic. So that's a really well part of this. They are stochastic, they are independent, so we can have direct computing parallelism in it. So don't be embarrassed by this. It's not embarrassingly parallel, it's deliciously parallel. It's a matter of point of view. It's important to have that in mind. You want to be in the case that everything is scalable right now. It's really better to have that. But usually it's not that simple. Because we can say, okay, I have a bunch of events, but maybe they don't fit in my memory because they are too big, or I cannot express as many parallelism as I wanted on this event, for example, because they are complex, or they are maybe just too big for a CPU or for a GPU, for example. They cannot fit in the cache, or they cannot fit in the VRAM, or can have a lot of problem with that. So to express parallelism with this problem, I have to break down my events and say, okay, maybe my events are composed of pixels, just captors. So I have pixels, I have parameter, I have cells, I have whatever. So I can break down my events into small pieces, and then I express much more parallelism with that. So whatever the number of pixels I have, it's fine. But maybe it's not enough. Maybe it's still not enough because pixel, we have too much data in the pixels or whatever, and maybe we have a time response on the pixels. So we have slices or waveforms or pulse of whatever you call them. You have an extra dimension. So in this schema here, you see that we can have a nice tensor to work with. But the problem now is, okay, I have a tensor, it's really nice. So as Adrien explained to you, and Vincent and Sébastien and everyone before this presentation, do not use classes of classes of classes or structure of structure of structure to do your computing, because you will kill your performances. Just use simple table in a large way. But the problem is, okay, but how do I store my tensor now? What is the order of the axis? Because right now it's nice, but how do I do that? And the way to do that is actually really simple. You have to think about what I'm supposed to do with this tensor. So let's see. Okay, for example, maybe the first step is calibration. So we get, for example, voltage in each cubes here, and we want to convert this voltage into photons or to energy or to whatever variable you want to use nicely in your analysis. So let's say for this purpose, the purpose of this presentation, even if it's not really the case, at least for CTA it's not the case, but for this presentation, let's pretend it's independent of the computing. So this means that whatever the order of your data here, you can compute your calibration, everything is nice. No problem of performances, no problem of vectorization, parallelization, GPUification, everything is nice. Okay, why not? So if it's not the case, you are stuck with this one. If it's independent, you can say, okay, the first one is independent, the first one doesn't care of the order of the data. So let's have a look to the second step. And the second step might be integration. So for example, we want to sum all these slices here with a weighted sum, for example, but a weighted sum is at least a sum. And we want to reduce this axis to one element. So we perform basically a reduction for that. And once you perform a reduction, you have to remember of Adrien, of the presentation of Adrien with the CPU architecture, you have a back dependency. So we will see that in detail after that. But right now, a back dependency implies that you don't want to sum this element with this element directly. They cannot be contiguous. If they are contiguous, we will have a problem of performances because you will have to wait for these two to be computed to have these two and etc. And that's a problem. If you do that, you cannot vectorize if you do that. So in a really nice way, you can say, okay, I cannot vectorize on this side, on this axis, so let's use the contiguous data. So the last axis of our tensor will be on the pixels. So that way, we can sum the first row here to the second row here, and the third and the fourth, and etc. And everything will be vectorized, no problem. Because we assume in this also in this part that we have much more pixels than we have slices. If it's the opposite, maybe you want to trick also stuff, but normally you should prefer this axis even if you have less pixels than slices to be sure that you can vectorize. But maybe with some padding and stuff like that, we'll see that later. So the good point, if we can vectorize, so it's nice. We can also vectorize the integration with which is really good. That's the point, the main point. We can also vectorize the calibration because the calibration does not care of the order of the pixels or the order of the data in general. So everything is fine. And so naturally we can say, okay, the second axis will be on the slices, because once we sum two rows of pixels, we want them not too far from each other in the cache, as Adrien said in the CPU architectures part. So naturally we have this second axis, which is this one, and of course the first axis will be on the event. And on the event we can do whatever we want. We can spread on cores, on nodes, on cluster, or whatever we want. Everything is fine. So we have a nice design for our data, so now we can work. So this is important. If you have one thing to remind for this presentation, it's computing drives data storage. You cannot have efficient computing if your data storage is random. It's not possible. You have to take care of what you want to compute to ensure that your data will be stored in an efficient way for your computing to work with. It's really important. And if we do that, now we have a really good basis. So for CPU, GPU, whatever we want to use, everything is nice, so no problem. Let's have a look at what we can use for standard C++, for example. So in C++, for CPU and GPU, if you want to use CPU, for example, you can use building blocks, which is a parallel library of Intel, which is really nice to use. And on the GPU, you can use Thrust, you can use CUDA, and you can use many other. And if you want to do both, you have a lot of choice. You can use Cocos, you can use Alpaca, Cycle, OpenCL, OpenSCC, a lot of library, old, new, standards for cycles, for example, non-standards for others. But yeah, the problem with that is, personally, my crystal ball is out of order. So if I pick one, how can I ensure that it's the right choice, right? It's quite difficult to see, especially at this point right now. So, okay, let's try to not pick one and to do another stuff. Of course, you can say, yeah, whatever the problem, I can define a nice interface between my problem and the application. For example, if you want to have nice portability, you can express your computing with matrix product or linear algebra in general, because all this library could get you some linear algebra, and you can use, for example, the MKL on the CPU side, you can use cuBLAS on the GPU side, and everything is nice. The interface are quite the same. You can unify the both interfaces in with a nice wrapper. And for you, it's transparent. You do a matrix multiplication, whatever the hardware, and everything is fine. But if you want to go deeper, we need a bit of help, in fact. So for the CPU, for C++, we can use compilers, so GCC, G++, etc. compiler, and LLVM compiler with Clang++. And with C++17, they can use directly TBB. And in fact, it's the same for DPC++ and NVC++. So they all use TBB as a backend for the parallelization once you want to express parallelization in C++17. So no need to use OpenMP or stuff like that. You have TBB, which is the official backend for all these compilers. So it's really nice to use, in fact, because you don't have to worry about that. And the funny thing is you have exactly the same performances at the end, because at the end it's a TBB backend, so you get the performances of TBB, whatever the compiler on the top of that. So it's really nice to have it. And since 2020, we have the same with C++17 for NVC++, so you can use directly C++17 and run on Thrust behind the hood, but it's totally hidden for you. And you can use GPU without taking care of whatever languages you want to use, Cycle, Alpaca, CUDA, whatever. You don't have to worry about that because the compiler handles that for you. And it's really nice to use, in fact. It's really, really powerful. So, that's the point we want to keep in mind, but it will be for several webinars from this one. Now we will focus on the CPU part for this webinar, but we will have the GPU part of this webinar a bit later. in the schedule of the webinars. So this is a standard unification, and this is really powerful. So we will explore a bit what we can do with that on the CPU part first. So let's start with an ADAMA product, because you know I always have to put an ADAMA product in an example when I do a presentation. So it's an element-wise operation. So we want to multiply x by y and store the result in the z vector, so element by element. And in classic C++, we want to write something like this. So we iterate with a for loop and we do the computation and everything is fine. And here we can wait a minute and say, yeah, but we have extra information here, because at least this is a product element by element, and we don't need the explicit order of this operation. It's not mandatory. We can do this computation without the ordering. If the element 42 is ready before the element 3, it's not a problem. At the end of the day, if we have the computation ready for everything, all the elements, we don't care about the order of the computing. So yeah, it's not really okay to specify an ordering in this part. So we can use C++ and we can use a std transform to say, okay, I want to compute a lambda function. So here you have tab x for begin and end, so with iterators, and we have tab y and the result here. You pass a lambda with the two input x and y, and you return the result in the tab res, and you do your ADAMA product, and everything is fine. And nobody cares about that because it's an horrible syntax and you can do nothing with that. So me as first, I don't use that because it's horrible. But in C++ 17 we have an extra argument in it, which is execution policy. And the execution policy will tell the compiler, okay, but I want to execute it in a sequential way, a non-sequential way, so potentially a vectorized way, a parallelization algorithm, so maybe we want to use threads, or a threads with vectorization. It's also possible. And it's really powerful. So you express this stuff and you're supposed to get performances. If you use unsec, for example, or parunsec, you will have all the parallelization of the TBB library, and you will have also the vectorization behind it. So it's really powerful. So let's try it. But before that, I will explain to you how to vectorize without this, because this is a game changer. So how to vectorize and what is vectorization, of course, before that. So as Adrien said in this presentation on the CPU architecture, so vectorization, the idea is to compute several elements at the same time in the same cycle, if you want. And for example, on SSE4, so in 06, you can compute 4 floats at the same time. In AVX, 8 floats at the same time. In AVX 512, 16 floats at the same time. So it's really powerful, but you have to make sure that this can work. So you have the scalar operation and you have the equivalent with the vectorized operation. So here for AVX, for example, here we have 8 values. We perform one operation and we do all the 8 operations at the same time. So it's really fast, and we can get, for proc CPU info on Linux, you can get your architecture here. So if you have AVX, AVF, AVX 512, you mostly have AVX normally on your laptop. On server, you should have AVX2 or AVX 512 something normally. And the same on Mac if you have an Intel CPU. So if you don't have an Intel CPU, you should have something weird here normally. But you can have a look also with that. So to vectorize, we need to ensure the compiler some stuff. So first, we need to have contiguous data. So we want to be sure that in a vector register, we have the same data to perform the same computation, so the data type, or the meaning of the data also. So for example here, if I have random values here which are not the value I want to compute, because I have a structure or something like that, I cannot vectorize. It's not possible. It will be really bad. You can force it if you want, but you will not get performances, so it's useless to force it. You have to stay in the nice way here to be sure that we can have performances. Then you want to align your data. So you don't want to use a malloc or a new. You want to use a memline or a POSIX memline or a std-align malloc in C++17 to ensure that you will allocate your table in a border of a vector register to be sure that everything will be nice. If it's this, if you are in this case here, so you cannot vectorize. If you lie to the compiler and you say, okay, I can vectorize, you will have a segmentation fault because this data do not belong to you. So maybe another application, maybe you will have a crash, maybe you will read random values. If it's yours, maybe not. Maybe you will write on random values on your data space. So you don't want to do that. And here you have another vectorization on align data here. So it's nice. So you want to change your way to allocate your memory. So it's not that terrible, but you have to think about that. But it's not the end yet. Because now you have to ensure the compiler that if you put some pointers so to do a computation, the compiler can think about that. You have a table Y which is overlapping the table X, so you cannot vectorize. You can have conflict, you can do some computations or read, but you want to do a read and a write at the same time, so at the end of the day you have a back dependency, also again a back dependency, so you cannot vectorize, not possible. So you have to use the restrict keywords to ensure the compiler that I promise to you tab X and tab Y belongs to two different memory parts in the system. So they do not overlap, everything is fine, no problem. You can trust me. Of course, if you are lying to the compiler, we'll have also a segmentation fault or crazy result of stuff like that. And it's still not the end, because now we have to ensure the compiler that everything is aligned. So we align the vectors, but now we have to tell the compiler that, of course, we have aligned vectors. So everything is fine. So we can use the std-align now with C++17. It's a built-in function of G++ if you want to use it, but it's more portable if you use std-align. Yeah. You can use macro vector alignment here to say 32, for example, for AVX2 or 64 for AVX512. It's better to use a nice algorithm to get the vectorization, to have the size of the vector register. Here I do a simple way. You can use it in a proper way. The important stuff is to have a vector alignment set at some point here. And if you do everything, it's not the end yet, because you want to tell the compiler to vectorize. So you want to say, okay, O3, I want to have nice optimization. I want to F3 vectorize, so I want to vectorize, activate the vectorization. march equals native, so I want the binary to be used on this current architecture, so the host architecture. So you can enable more optimization if you do that. To specify it, and for mtune the same. So for the optimization, you want the optimization valid for only this CPU and not every CPU in the world. So it's better. And MAVX2, which is now not needed with G++11 as soon as you have march equal native and mtune equal native. I like to let it in the command line to be sure that I'm compiling on what I think I'm compiling, especially if you want to compile on AVX2 but you are on AVX512 or the opposite, for example. It's nice to have that in mind, but if you have a recent compiler, so G++11, 12, 13, 14, you don't need to put it in the command line. But it's always nice to be able to change that if you need it. And if you do everything with, so here I have an asterisk malloc, but it's a custom align allocator here. if you do everything, you can vectorize, and everything is nice. It's a lot of work. And on the code correction, you have this kind of stuff. So with the built-in assembly line here, the restrict keywords, and the for loop here, which I thought about in the very beginning of this presentation. So in terms of performances, if I use O3 computation with no vectorization for now, and then I add the vectorized version by hand, so the one I just presented to you. So I got my stair step here, so it's nice. Here I'm in the L1 cache, here I am in the L2 cache. So I have a nice vectorization, everything is fine, no problem, it's nice. And if I use the unsec in O3, so without asking to vectorize, I get some improvement, but it's quite the same performance. This is totally normal because we get only O3 optimization. If we ask the compiler to vectorize on AVX2 here on my laptop, we get potentially the same performances as we did before with the same vectorize part. But here there is a trick, because I do not need for the unsec to have aligned data. It's better if I have aligned data, but it's not mandatory. I can vectorize without aligned data, but it's not possible with the previous version, with the Adama product vectorize here. So it's a win in a sense. So I don't have to align my data. I don't have to promise to my compiler that I have aligned data. I don't have to use a restrict keyword because I use directly vectors. So it's really nice. It's really nice to have that. And with we can align data, of course, because it's possible in std vector to change the allocator. So if you change the allocator on your std vector and you say, okay, I want a custom align allocator, so it's really simple to do one of them. You can align your data, and then you have much more performances because you don't have a pill. So I don't want to go too much into detail here. We will get the detail in the school, or if you want to ask, we can go into detail in the question. But it's better, of course, if you have aligned data in this case. But it's working even if we don't have aligned data. So it's really nice. You don't have to be bothered with all the things I explained to you before. You just have to use unsec, and that's it. Done. It's really nice. If we compare, for example, G++ and Clang, so G++11 and Clang 14, so with classic optimization flags, so 01, 2, 3, and fast. First, we can say, okay, but it seems that O2 in Clang is better than O2 in G++11. It's not really like that. In fact, we will have a full lecture on that on the school, but shortly, they just disagree on what is supposed to do O2, O3, and OFast. So O2, O3, and OFast are not so intrusive in G++11, and they are really aggressive in Clang 14. So this implies that if you don't pay attention, you will say, okay, I have better performances with Clang than in G++, but it's just because they disagree on what is OFast or O3. It's not because Clang is a better compiler, it's just because they disagree on the flag. It's just that. But for the other, it's perfectly the same. For O1 and O0, it's the same. But for the most optimization flag, it's not the same. Just a matter of compiler. But if we vectorize, here we get the O0 for comparison here, but we get the same performances at the end, because when you get the best performances possible, you get the best performances possible, whatever the flag you pass. So at the end, if you ask to get the best performances with all the flags I just give you before, it's efficient. No problem, no matter of compilers, everything is nice, no problem. So let's try with SAXP, so A times X plus Y. That's why we call that a SAXP, so it's single precision AX plus Y. If you see a DAXP, for example, it's a double precision AX plus Y, etc. So it's still an element-wise operation. We still can express that in a C++ for loop. we still do not need to explicit the order of the computation, because whatever it's the order of the element, at the end of the day we want to have all the elements computed, that's it. We still don't care about the STD transform algorithm because it's horrible, but we need to copy the A when we catch the variable outside of the lambda. And on C++17 and C++20 we want to use the execution policy, and this start to become interesting with a sec and sec, par and sec possibility. And with the same stuff, so they still disagree, both compilers still disagree on the performances we should have on O2, 3 and OFAST, even if they get closer now. And with the vectorization, it's really nice. We have the same performances, it's totally normal, no problem with that, everything is fine, and we don't care about all the stuff that I presented to you before. You just use the uncheck and the vectorize option for the compiler, of course, because we have to tell him to vectorize, but you don't have to worry about that in your code itself, so it's better. Let's talk about reduction now, because it's a bit more tricky. As I said before, once you heard reduction, you want to think about backdependency. And backdependency means you have a problem of performance, always. So let's see how we can do that. So if I do that in C++ with a float, so I sum my values like this, for example, here again, every time you do a reduction, think about Vincent. You don't want to sum 1 million or 100 million of elements like this, otherwise for sure you will have a wrong result. Here I assume my number of elements is something like several thousand, maybe, not more, so the result will be nice. I assume that I have also nice condition value, so normally everything is nice. So I can do this computation. Of course, if you have only denormals, if you have really bad values or none or whatever, or you have big and small values in the same computation, of course you will have wrong result. Even if it's O0 stuff, even if you think that since it's not vectorized, it's the reference, this is wrong. No doubt about that. So here I want a chunk, my number of elements is several thousand, so I can vectorize. And also here it's not always right. So here we'll start and say, okay, the order is not necessary. And again, have a look to the presentation of Vincent about precision, because if you start to sum values and for the beginning to the end and from the end to the beginning, you will see that if your data are not well conditioned, you will have difference of result. So here I assume that I can for the purpose of this example, but if you do want to do that in your application, you want to be sure that you can. It's important to be sure to have right result. So in C++17 and C++20 we have the std reduce with the execution also par and sec. So we said we want to reduce the vector x and we want to start from 0, and we use std plus to sum the values. We can use std multiply to multiply all the values, whatever you want to do, no problem. And with the performances here, we have different performances with Clang and G++11. So again, they disagree a bit on the optimization we want to do. And if I vectorize, they are stuck. They cannot do better than this. They are stuck. And it seems that it's the end of the day, but it's not the end of the story yet, because I want to push it a bit further. And if I compute that myself with intrinsics, so when I say intrinsics, it's a bit of abuse, language abuse, because I do not use real intrinsics, so the very function that inlines assembler in the compiler. I use a library on top of that to be able to call all the intrinsics I want. So it's my library, but you can use XSCMD, for example, which can do the same if you don't want to write your library, this kind of library yourself. Or you can use EV, or of course, if you want to do that, it's really nice. So here I express my computing with simple intrinsics, with these performances, and everything is nice. It's better, at least. It's really better than the performance I have before. So this is about the back dependency. The first point is about the back dependency inside the loop. So it's a bit tricky with the internal representation of the compilers, but they cannot do the optimization that I do here. So that's why they are stuck here. I can push further here. But I can push even more. I can say, okay, I want to do my reduction. I do my reduction with the align version. So here, with the C++ unsec here, and the other here, with the reduction with intrinsics, and we can get the practically the same performances here, and even better of my implementation. So this start to be interesting, because here we said I want to vectorize. I don't have an explicit order for my reduce, and I can have better performances than the one I can have by hand, if you want. So it's really nice. It's really nice to have that. But still, it's not the end of the story yet, because I can push a bit further also. But this for this one is really better, because if you use a default loop, you will get these performances. If you use std reduce with unsec parameter, you will get this result. If you can use it, of course. If you cannot, because you don't have well-conditioned data, you care about the ordering because you want something really precise, don't use that. But if you can, if you want to have a look, if you want to test, check that. It's really powerful. So here, the good point is we can do better, quite the same or better, than an expert can do with intrinsics, with a simple way. But as I said, I can push further. And I can do this one with an interleaved. So, for example, interleaved, compiler cannot do interleaved. Interleaving, it's not possible in this representation. The graph mathematics forbids compilers to do that. But I can, because I am a developer, so I can. So we can push also forward the performances. So how it's possible? How we can optimize a reduction? So as Adrien said in his presentation of CPU architectures, once you compute something in your CPU, you will have to wait an elapsed time until you can get the result. Whatever the computation is, even if it's vectorized, you have to wait for the result. And of course, if you sum values like this with one accumulator, you will wait a lot to get your result ready. And this is what we call the back dependency. You have to wait for your result until it's available to compute the next element of your computation. And that's annoying. Let's be honest, that's annoying. So we can have a trick and we can say, okay, but I want to use two accumulators. So I use the first one and I wait for the result to be ready, but I change the accumulator during that period, and that I accumulate with another accumulator here, my computing. So I cannot do both computing at the same time, of course, because you have only one unit to do the computing, even if it's vectorized, of course. But I can wait just after this one to be finished. I can compute the next accumulator. This one is waiting, whatever, no problem. And this one is ready. And I still have to wait. But of course, I can increase the number of accumulators. And I can say, okay, here I am waiting a lot, but I can compute several steps at the same time, several accumulators. So in this little example, I interleaved 4 times, and I can compute each time I can compute a result, and no problem with that. And it's quite the same size here. I have roughly a speed up of 4, not totally, of course, because here's a really simple small example, but on a long example where this end and this start becomes negligible compared to the whole computation, it's really good. We have a lot of performances for that. So this is really interesting. So we can still push a bit with the intrinsics approach, but you can get really nice performances for that, and it's really important. So with the reduction of intrinsics, so we start with the vectorized version, we get the intrinsic one, so I presented before, the interleave with 2 accumulators, the interleave with 4 accumulators, and the interleave with 8 accumulators. By the way, you can say that 4 accumulators on 8 is the same for G++11 because it understands what we want to do and does it for you. For example, you can see that, okay, I have 4 accumulators, but I can unroll the 4 accumulators and I get 8 and you have the same one. Clang is not smart enough, and we have to explicitly say, okay, I want to have nice stuff. But it's possible. So since the very beginning of this presentation, I talk about triadic. So this means that x plus y, for example, is a triadic. So we have 2 operands, 1 operator, and we put the result inside 1 resistor, for example, or one table. That's why, remember that Adrien said to you in the CPU architectures, that's why we can read twice more data that we can write because of triadics. We want to write 1 result, but we want to read 2 operands. So it's bad if you want to read only 1, but it's designed to be readable for 2, 1, and everything will be efficient that way. But if I have a quadratic computation to perform, for example, x plus y times z, for example, it's really simple to do that with classic C++, no problem. But with C++17 and above, we have to use a trick which is not really elegant, which is a vector of index here, and we iterate over the vector of index and we perform the computation like this. The point is we have to use std vector, otherwise it's not vectorized. So it's fully vectorized, it's a good point. We need an extra table, so it's not really that elegant, unfortunately. It's not vectorized if you use std for each, so you have to use the std transform, but I think it's a problem of backend at this point, not a problem of the compiler. And it's not vectorized if you use pointers with vec(x) and vec(y), so we have to pass vectors, or reference of vectors at least. And if we do that, we have these performances with G++13. And with the G++13 we get that. I was really disappointed when I saw that, because the vectorized performances is this one of the worst one. Quite horrible. Okay, what's going on? If I ask Macao, he said to me, okay, there is too much branching and we have data copy. When we catch the variable, we have a data copy. Sounds not so great. There is a problem. We have to figure out how to solve that. So if we ask Macao, we have plenty of hint, and he will say to us, this one is not vectorized. So the pointer here, when I pass a pointer, I said to you before, it's not vectorized, but it's faster. Because I don't have data copy. I don't have lots of branching for everywhere. So it's really nice to have it. But yeah, it's not vectorized. And the last one is a trick. It's vectorized. It's a good point. The TMP stuff. But of course, it's vectorized, but I use a trick. I use a temporary vec xy to compute x plus y, and then another STD transform to compute x plus y times z. So it's not super elegant. You have to break down, you still have to break down your computation into triadic. I'm pretty sure at some time we will have a library to do that, but for now it's not the case in the backend of the compiler and the standard library also. Even if they use TBB, it's not possible right now. I think it will be possible at some point, but not right now. So that's a bit annoying. But we can use view transforms with the triadic computation. So here it's a time and two times. So we get this kind of stuff. So with that, we have a STD view transform. We declare a computation with a zip. So we zip vex x and vex y, for example. We get a tuple. We say, okay, the tuple, we want to expand the tuple and multiply x by y here for the two first here. And then I pass the view xy here. I iterate on it. I pass vex z and I do xy times z, and that's it. Okay, it's not that bad. I can also do this kind of computation here when I zip 3 of the vectors here and do my computation only here, and here I execute it with the execution policy because there is no execution policy in the view, and we can see what's going on. So no extra table are needed, so it's quite elegant, let's be honest. It's really quite elegant. But it's not vectorized yet because of the STD view zip, because the zip, it's a tuple inside it, and the compiler considers it as contiguous elements, and it's not working. So it's compiling, so I cannot blame G++13 because at the time I did this test, it was the only compiler which can compile this kind of stuff. All the other do not compile. This was the only one, so at least it was compiling, but it's not vectorizable because you think we are in this kind of configuration, but at least we are in this one, but it cannot understand that yet, unfortunately. Let's talk about G++14 because we have new stuff coming on. So I redo this test on G++14 and I put some reference. So these are the reference we can do in C++17 with align vector and vectorization for x plus y times z. So it's FMA if you want. Yeah, I changed a bit the computation. And these are not vectorized. And Macao said to me, okay, they are limited by instruction throughput. So too many instruction throughput, they have to compute the index, the reference, the stuff like that, and it's cost a lot, of course, because we have an injection table, and the compiler cannot say, okay, it's an injection table, so I can read whatever data possible, so I cannot optimize that. So it's smarter than before that everything was vectorized, but the computing was horrible. Here the computing is horrible, but it's not vectorized because the compiler says, okay, no, it's not possible. Let me alone. It's not possible. So with Macao, I get this kind of information, and these are not vectorized, but there is no data copy. So the black is the view unseg, so with the view for y and z with the zip, and the transform then for the addition with x of this view. And the purple here is the unified view full, so you get one view transform with the zip with x, y, and z, and then you pass only a transform and say, okay, I want to vectorize, and that's it. And you see that it's faster, a bit faster, not that much, but a bit faster than the pointer version, where I catch the pointer and I get my index. It's quite okay, and maybe there is an index behind the hood, let's be honest, but it's not vectorized yet. It's a bit bad, but it's a bit sad it's not vectorized yet, but it will be possible at some point, I think. There is a last test I didn't perform yet. Maybe we will see if I have time to show you the very last one I want to perform on the school, but it will be for the school. I don't want to be too long on this right now. And this is a vectorized approach. So again, with 2 temporary and 2 acid transforms. So it's not perfect, but it's still quite close to the one we had before. Of course, we use much more memory, because we have an extra table, a temporary extra table that we do not need with this reference. That's why we have a nice step here. But still, it's quite encouraging. It's not that bad. Could be better, of course, but it's not that bad. So we can see what we can do with that. So to conclude, STD algorithm for C++ 17, 20, and 24, they are okay for 3x right now. STD view transform, it's not vectorized yet because of zip. So we have to wait a bit for the backend to be a bit mature. And we can really vectorize really easily. And especially for the reduction, you saw that it was really performant, even if we can push further if you are an expert. But if you are not, you can really get nice performances with this kind of trick, and better performances than if you use a for loop. And you can compute on CPU and GPU, but we will see the GPU the next time. So in 1 month, something like that, I will see the GPU part of this presentation. And we will have normally a huge improvement because of C++ 26, because we will have nonlinear algebra in it. So it will be even better to use that. And they have to have vectorized transform view to ensure that linear algebra will be efficient. So normally we could get there on this point. So thanks for your attention, and I will get your question if you have some. Do you have any reference books to recommend on this subject? I pass a really lot of time on C++ reference, even if the documentation is not that clear. But I use mainly C++ reference, and I do a lot of tests because it's a really new subject. So there is no really books about that, especially on C++ algorithm. And I also can ask directly to Vincent Raverdi, which is a colleague who is working at LAPP, and is a reference also for the C++ committee standardization. So every time I have a big subject, I ask him. But yeah, it's a lot of tests. For now, it's really a lot of tests because there is no really way to do that. And you can use STD transform, you can use range transform, you can use view transform, you have lots of ways to do the same stuff. It's quite difficult to do that every time. Is the code available somewhere? We can make a world trial. Yeah, the code will be available on the lecture. In fact, for now, my lecture is not really finished yet, but everything will be available. I think for the school, maybe not before, because we want to keep the surprise of some stuff. But yeah, everything will be available. You will have full test. I have a dedicated test for this kind of stuff. I have all the tests in my lecture. So yeah, we will definitely have that, and we'll do the same kind of trick for the GPU also. The GPU computing in a bit more than 1 month for that. Do you have the source code of your test in presentation to be shared? Yeah, the presentation will be shared. The source code, I think I can. I prefer to keep that for the school, but yeah, if you really want to get the code, maybe you can mail me and send you the link. But I prefer to keep it under control for now. But I have lots of tests. I present to you some of them, but I have a lot of tests for that. Do you test on the laptop or HPC? Both. Here for this presentation, I mainly test on my laptop, but we test also on servers for the computing. So inside containers, because it's not that easy to have a G++14 available on bare metal installation. But yeah, we do this kind of stuff also. So yeah, it's not that easy to get all this information because the documentation is not really clear. When you go to some forums or stuff like that, people, they are not really, they do not really know what they are doing, because nobody really know what we can do with that. And so yeah, it's not that easy, but yeah, normally we can expect to have a better backend at some point for that. How do you feel the downtime difference between using STD and using OpenMP or manual threading? For me, it depends what you want to do. For all the example I tried, it's really nice to use TBB under the hood without knowing it. In fact, it's really nice. For me, it was really nice experience. You don't have to start your STD thread. You don't have to stop them. You don't have to take care of that. You don't have to use your Pragma OpenMP4 Parallel 4 to be sure that everything is nice. You don't have to link to a lot of stuff. You just have to link to TBB. That's maybe quite annoying point, but you can understand that. It's because the compiler doesn't know where the TBB library is, so you have to link once you compile. The problem is it's not clear. You want to use a STD algorithm, you pass the parallel flag, and then it will crash because it tried to link to TBB and you were not aware of that. So, but yeah, no, I'm get used to, and I use TBB. It's really nice. In fact, for the production pipeline we use TBB now in official backend for the parallelization. It's really nice to have it. And the point is, the threads of TBB are really aggressive compared to the threads that we can use with STD thread, for example, or OpenMP threads. So yeah, TBB is the threading building blocks. It's a parallel library of Intel. So the library which is used under the hood once you compute some C++ 17 stuff with STD transform and so on, with G++, Clang++, DPC++, or NVC++, you will have TBB, which will be used under the hood. That's a great unification, in fact, to have this kind of stuff available in the compiler. And in fact, they just agree on that, and they say, okay, let's use TBB. It's really nice. So maybe they use TBB because it depends. Yeah, TBB, it's one TBB now because they changed the name, because they always change the name of something in Intel. But yeah, TBB is one TBB now. If you want to install the package, it's one TBB dev to get that. Yeah, and NVC++. NVC++ uses one TBB, yes. NVC I didn't try, but NVC++, yeah. Does it solve the compatibility of the thread libs? So Sebastian asked. For me, it was not an issue. We can run on everything. I didn't try yet on ARM. So normally TBB should run on ARM. It's supposed to be possible. I didn't try yet. I want to try. In fact, we want to try for the school also. We will have some part on ARM on the school. But for now, it's not that clear. But normally, I think if compiler people use TBB, it's for a good reason, I hope. So normally should be possible, but we have to try to be sure of that. Do these algorithms support OpenMP? I'm not sure. Maybe you can trick the library to use OpenMP, but for now it uses TBB by default, at least. Maybe if you have a dedicated backend for that. In fact, we try also with a colleague to get all the backends. So for C++, for Vulkan, for TBB, they are all coming from the backend of Vulkan. Even for the backend of Thrust, for example, to do this kind of computation is the same. Everything is a copy paste, particularly of the previous one from 2018. So yeah. But I'm not sure there is a backend for that for OpenMP. But maybe there is one. But we will have the comparison during the school between OpenMP and TBB, because we will use both libraries for the computation. So, but at least, yeah, using TBB is not that very complicated. You use your OMP parallel 4, and then you link with -f OpenMP, and normally that's it. So it's quite nice also to have that. But let's see if there is a smooth way to do that. From Sebastian, have you some ways on that path to do cache blocking? I think yes, but the the functions are horrible. You have the std view chunk, you have the std view stride, you have the std view, I don't remember what, which you have plenty of that to do this kind of stuff. I didn't try much, and the problem is on C++ reference we get particularly only example about strings, but nobody cares about strings. Come on, we want to do computing. So you can get some views of elements. You have also std adjacent transform or view adjacent transform, I don't remember. To get you have an element and you get the two neighbor or n neighbor of this element, and you do a computation about that. So it's possible to have that. Maybe it's a bit young for now, not really mature. But normally you should be able with a vector to slice it with a std chunk or view chunk or chunk view. I don't remember that, but yeah, it's a std views chunk normally to chunk that. And then you have the opposite, which is the name are horrible to remember. That's a big problem. So chunks to slice, it's and you have another way to join, maybe std join to put the chunk together to rebuild your vector of the start. It's possible. That's maybe a problem also for the std adjacent transform. It's only one dimensional. So once you want to have a stencil with 2 dimensions, it's complex because you have 1 dimension but not the other. So you have to do some tricks to be sure that everything is working. It's a bit annoying. But yeah, we will have to wait, I think, for the presentation of Joel to get the same kind of stuff for Eve with normally no problem. But yeah, MDSpan is not that good. And we definitely want to have multidimensional iterators to do that in a simple way, but it's not that good also. So, but normally at some point should be working, but now not really good. And the other problem also is once you want to compute with std views or std ranges, and you want to pass your std range transform result inside the std transform and start another stuff, at some point it will break, it will explode. You will have 1000 line of error, which is really difficult to see. But I think it's because the compiler are really young on that topic also, so it's not that simple. But yeah, it's quite difficult to know what's going on, what to do, what to fix to make sure that it's working. I tried yesterday also to use std range iota view to get the index in the order, so you have the guarantee that everything is ordered. So the compiler should do some optimization well, and it's not the case yet. So for now they cannot exploit the fact that I pass, for example, a range as ordered range. You can also have std enumerate, the same enumerate as we get in the Python stuff. So you pass your enumerate view, and then you have tuples of your element, the index at your element, as in Python, in fact. So you can use a lot of stuff for that. But yeah, they are really new. Sometimes every time, particularly I go on C++ reference, I see new stuff, and I say, okay, we have new function which we can use, but how to use them? The documentation is horrible, let's be honest. And every time it's a matter of okay, what I can do with a string, but I don't want to do stuff with a string. I just want to compute stuff. So yeah, it's not. Maybe it's not the priority right now for people of the standard library, just to get things working, and then maybe for the optimization later. So maybe it's a bit too young for now, but from Sebastian, question from Sebastian: how clear or readable are the call stacks in GDB or profiling tools? it's you see there is a lot of trick behind the hood. So you have your call, and then you have a bunch of stuff which are coming from the standard library, and then from TBB, and then a lot of other stuff. And so at some point you get your lambda function, and you say, "Oh, I know this function; it's mine." But yeah, for now, maybe it's there is no hiding part of the call stack. So could be a bit complex to get that, but yeah, it's really young, as I said. So yeah, it's not. Yeah, Adrien said in perf profilers, both C++ and Rust have the problem with long generic type names. Yeah, that's a problem. In fact, it's mainly the problem also for that. It's your computation becomes a type. So all your call with your transform, your execution policy, the parameter you pass, the lambda, the parameter of the lambda, the output of the lambda, everything becomes one type. So you have 3-4 line types, and the compiler is yelling at you and saying, this is wrong, you don't get the right type, and you say, where is the problem? Help me, please. Yeah, it's... in fact, it's quite the same problem that we have for the expression template before, and which was a mess every time we have a problem, and now they fix it in the compiler, and we don't use this thing too much also. So normally should be okay. Yeah, David said if it's also true for us, C++ is forgiven. Yeah, it's quite complex, in fact, to deal with computation, and you express your computation via a type, and then you can do some optimization on it, but the backend should be smart enough to do that. So yeah, it's quite difficult. It opens a lot of doors to make optimization, but once you have a problem, yeah, you yeah, it's difficult to get the information. Well, if we had Python and Fortran for the comparison, yeah, at least yeah but yeah, for Python and Fortran, once you have a big error, also it's that's the problem once you start to use complex stuff. The one at the moment it breaks, you say okay. Yeah, it's a limitation of this language. Every time you want to do something complex, you have an error exploding on your face, and you say, okay, let me put this error into a file, and let me scroll it into 1,000 of screen to get what's going on. Yeah, it's quite difficult. Yeah, it's the price you pay to have clever compile time types. But on the other way, you use type to be sure that you are doing something you expect, and if it compiles, then the result should be okay. So it's really nice also to have this kind of stuff. But once you are not really reasonable with this kind of stuff, it explodes. And yeah, the point, maybe I even wrote a program to summarize C++ template names in the past. Yeah, it was too much trouble to maintain because C++ syntax is horrible. Yeah, it's quite not simple, but in fact, it's quite also nice to have this kind of stuff to be sure that you have the right type and you do your right computing on the right type, so you get the right result. To be sure that it's possible, everything is nice. So to avoid this kind of stuff, what I do in the software that we develop for CTA is to use dedicated backend for this kind of computation. So if we have an explosion of error, it's only in this backend, and if the backend is compiling, everything is done with a nice interface, and I just call the computation and everything is nice. So it's avoid, if you do that everything in the main, you will have an explosion of problem. If you do a nice backend which does only that, you can limit the problem to the specific computation you want to do. And if you have a problem, it's simpler to get the answer of why you have this problem and how to solve it. Again, a lot of design. We will bother you with the design during all the school and during all the webinars. It's important to have a good design, to maintain, to be able to refactor, to add some functionalities, to not be stuck between a big wall of problems. So yeah, it's important to have a good design. Okay, I think maybe we can end this webinar right now. Yeah, okay. The thanks are coming up. So yeah, thanks you for attending this webinar. So next week we will talk about Rust. So Adrien will give you a presentation about Rust, so how to use it for computing purpose. That's the main point of his presentation. So to present the language, how to use it, how to compile it with cargo, with all this kind of stuff. We'll have also a presentation. So for the week after, we will not have presentation because it's GTC, and the week even after it will be GPU architectures. So have a nice week. See you next week for Rust and presentation from Adrien, and have a good day.